Okay. Can we do that in a single reaction? Okay. So, what do you want to do?
I guess take out the OH first.
Okay. How do you want to take it out?
Maybe elimination or having it just attached to other hydrogens, please.
It's really dry. I should pause the recording. Well, it's just sucking it right out. They're pretty brutal. So I should have rephrased the question, because what you went through and said was fantastic. Well, let's try and do this, and you started to list a whole bunch of different things. But you did say one key word within it that I did like. Instead of focusing on just all the bonds, you actually referenced what kind of reaction you could do. Okay? So if we're looking at our focus being, let's lose that OH, okay, if that's going to be our primary focus, loss of that OH, how could we lose it? Right? We could do a substitution reaction. Is that substitution going to necessarily be helpful to us? Why not?
You're replacing the OH, now you make that lead too.
Okay? If we're looking at our overall kind of chemistry flow, our chemistry is moving kind of downwards through this reaction cycle. Okay? We're shifting it from being at that top carbon to somehow the bottom carbon as it's drawn. So if we're doing a substitution, we aren't shifting that chemistry at all. All we're doing is keeping it lockstep where it was. Okay? Which we might need to change it, but let's focus on actually trying to get it to move first. Okay? So substitution doesn't make any sense. Addition doesn't really make any sense because there's no pi bond. Okay? Acid-base isn't really going to cause any chemistry to move. You could put a hydrogen on and off, so that's not going to be particularly useful. We hope and pray we don't have to do radicals, which I think comes true in this case, okay? Which means we really only have elimination left over. So would that be beneficial? If we somehow pulled off an elimination, what would we hope to have happen? Well, we'd hope our leaving group, our OH, to disappear, which would be good, and we'd have the pi bond there, which does mean we're introducing a new issue. That hydrogen would have to get removed. Okay? And then it would have to get put back on our structure. Kind of, sort of? Okay? If we did that elimination, that would cycle the chemistry down, which could be powerful, and then we could go through the exact same kind of thought process that we've been going through and say, well, what else needs to happen now? All right, well, if we look at this structure and compare it towards our final product, what changes would need to happen? Loss of that pi bond is going to be a real big swing on it. We're going to need to gain a hydrogen. Okay? And then we'd actually start listing out the same things that we'd already listed previously. Okay? We need to gain that OH and we need to lose that H. Okay? So without even thinking of reagents, can we now think about what the next structure would look like? Same without the pi bond, which means what kind of chemical reaction are you trying to run? Okay. I can kind of accept reduction because it is technically a reduction, but our reaction classifications aren't pushing towards reduction. That's where we'd be referencing our addition, elimination, all that fun stuff. So I like the switch up that you're now saying you're going to run an addition. And if we ran that addition, what would happen? Okay, and we'd now have to replace atoms within it. Okay, if we just straight up replaced with hydrogens, what happens with our product? It would look exactly like this. Do I have any chemistry now? No, which means what would I have to consider? Dun, dun, dun. Radicals. Do I want to do radicals? No, so let's not add hydrogens because adding full hydrogens across the board is going to destroy our chemistry and we're going to have to deal with radicals. We don't want to deal with radicals. All right? So when we run this addition, I don't want to add just 2 hydrogens. I want to add 1, okay? And that would be powerful. That would be the gain of the hydrogen all the way at the very beginning. Okay? That would be putting the hydrogen that I wanted on there. But what's the other spot that I would have to take it or be aware of? Say again? Not yet. That tertiary spot. Right? Because I'm doing an addition from that alkene. Okay? Well, what do I want to have be there? Okay? Again, if I put hydrogen, that's problematic. But again, we need to think about where we're going. Have we gotten the chemistry to the final position? No. If we look at our product, the chemistry needs to be at that next carbon. We aren't there yet. Okay? Which means I would have to do some more reactions, which means what do I want that green spot to be? I want it to have this reactivity still, that positive characteristics. So what might be a good thing to have added across that pi bond?
A leaving group, perhaps?
A leaving group. What would be a good leaving group?
Bromine.
Okay. Any of our halogens, so we could modify that out to a bromine. Okay. We can now run the exact same argument from this new structure up to our final product. What needs to change? I need the loss of the bromine. I still need the gain of the OH. Okay. Are those 2 things that I can do simultaneously? No. Okay. So again, focusing on where the chemistry needs to be, I need that chemistry to continue to move, which means what reaction should I try and run now? And if I run an elimination, what am I hoping can pull off? Lose the bromine and place a pi bond in there. By placing the pi bond in there, I've now completed the final loop that I actually wanted. I've got chemistry at that final position. That's good chemistry. Okay. Now what needs to happen? Okay. I need the loss of the pi bond. I need that gain of the OH back. And gain of a hydrogen. And if we look at that sum total, that looks an awful lot like what kind of a reaction? An addition. Okay. This sets us up with work that allows us to now think about what reagents could we use to navigate this process. Okay. What we're following is what are the changes? Where's the chemistry shifted and moved? Are we following a process that allows us to get there? Yes. To the question that's asked, provide the reagents, have you done that? None. Not at all. Okay? Which means you haven't answered the question at all, and then depending on where you would see this question and who's grading it would change how you would get points. Okay? I would argue what you've shown here is a lot of the process work behind this to explain what reagents you need. You just haven't crossed that last line. It's absolutely not going to be full credit. But the work here is probably half credit. Okay? You've recognized the patterns and the motives that you need to undertake to complete this reaction. Okay? The time investment behind that, according to this, was 9 minutes. That included me gagging down some pancake that was way too dry. Okay? So that investment-wise wasn't too bad. Okay? And again, we talked through it, not just let's write the answers down. Does that make sense? So investment-wise, that's not bad, and that can be worth an attempt. Okay. The next part is now knowing those reagents. How comfortable are you with your elimination and addition reagents? Okay. If you're comfortable, start swinging away. Okay. If you're not comfortable, that would be a good opportunity to back away. Okay, and say, I'm just going to move on and look at other things. Okay. There's some other thoughts that could come with this. If we look at these elimination and addition reagents, and in particular the functional groups that we've got drawn on here, do any of those functional groups harken back to the content that we have just addressed within this unit? was an interesting way to phrase all that. So let's try that again. What chemistry did we study this unit?
Chemistry?
Carbonyl chemistry is one way. We could look at the functional group associated with it. Okay? I'd take a step back from the functional group and instead of overemphasizing carbonyl and recognize what the carbonyl is a representation of. It's not a pi bond exactly. It's a polar pi bond. Are we looking at polar pi bonds at all in this? No. So what is this question now asking? Synthesis and how well did you remember all the stuff from OChem 1? Okay, I would argue Unit 1 of this semester. Okay, so it's a review question. Okay, if you don't feel you've reviewed enough, then again, that's something that you should let go of. But recognizing your weaknesses during an exam is a good thing. Okay? The hard part is letting it go and moving on. Okay? So cool. Let's start to swing at some reagents. If we go through and look, do any of those stand out at you of like, oh, I know that reagent?
The first one I think would be the 2-butyl.
Oh, is there a list of reagents?
Nope. Why would I give you a list of reagents, bro? No. T-but-O minus. Why do you say T-but-O minus for an elimination?
It's a strong base.
Strong base. Okay, perfectly acceptable. That is a standard thing to memorize for elimination. It's usually a pretty good thing. Okay, does anybody want to challenge, or we leave it alone?
I mean,
It's a bulky base, so
it's not going to
Okay, it's a bulky base. It would pick up outside hydrogens. Okay, so that could be problematic because what are we talking about? We're trying to remove that hydrogen, right? That's interior, so a bulky base could be pretty questionable here. Okay, so do you want to posit a change? Posit means offer. Give me something else.
heat and hydroxide.
Okay, so this is neat. So what we're doing is modifying the base away from the bulky base because trying to remove that hydrogen is probably not going to be very likely, okay, considering where that hydrogen is located. It's located very interior. The bulky base is probably not going to pull those off. You've added an extra layer to this and you throw it on heat. Why heat?
Because that favors an elimination reaction.
Cool. Elimination reactions also favor heat. Okay, so that could be a good thing. Are we good with that? Yeah? Okay, so now a question about logistics. Should we continue to go through and figure out reagents for all of these before we go back and be like, but, or should we do buts right away? Buts right away. It's amazing I still have a job some days. Okay, hydroxide is a great base. What do bases react with?
acids.
Which acids do they react with? The most acidic. So if we now go back and look at that starting structure, let's clean it up a little bit. Remove all that extra stuff. Where's the most acidic hydrogen in that starting molecule?
On the oxygen.
On the oxygen. What hydrogen were you trying to remove?
That one.
Not that one. Okay, that's a good answer. Or the one on the carbon. Okay, that's going to become problematic because what's going to happen? Our base is going to remove the hydrogen on the oxygen, which is then going to turn the OH into a negative oxygen, which then makes it a horrible leaving group. And to run the elimination, you need a leaving group. Okay? So this is a common memorization trap that happens more or appears more frequently in OChem 2 than it does in OChem 1. Because typically when we talk about substitution and elimination in OChem 1, we talk about it with alkyl halides. And the halides don't have this problem because the halides can only form one bond and it's to the carbon. They're a leaving group and we're done. It has no other chemistry. As soon as we throw in an alcohol, everything hits the fan and we got to be a whole hell of a lot more careful with how we approach things. Okay? Theoretically, this shouldn't be a problem for you Because in OChem 1, we didn't talk about it as just halides. We talked about it as leaving groups. And OH is a trash leaving group. You're going to be like, well, it's leaving into a solution of hydroxide. So it's not great. It's not bad. It's not horrible. Okay, but it's not great. Are we making a super stable product? No. In fact, our product is less stable than where we started, which means we have a bad leaving group and a bad product, which means
It's not-
it's not going to happen. Okay? So the use of the base, or that memorization of, oh, I need a base to do an elimination, is not true. Okay? You do need to remove a hydrogen, absolutely. And bases can help with that, but we have to be aware that there's other hydrogens that could be removed. Okay? So, what do you want to fix? That was a deep sigh, like you had something.
Well, the OH isn't a good leaving group to begin with, so don't we have to make that a better leaving group first?
Let's make the OH a better leaving group. Okay? So how could we make the OH a better leaving group?
Make it bigger. Add more stuff to it.
Add more stuff to it. Okay. How about we add a hydrogen to it? So what are you going to add as a reagent? Why would we do H2SO4 and not water?
Strong acid.
It's a strong acid. We add water. The water's not going to provide an acidic enough hydrogen to protonate that oxygen to any extent, which means we're not going to get that elimination. It's going to be kind of just mixing stuff for the hell of mixing stuff. The strong acid will go through and protonate. Why did you not say HCl, which is also a strong acid?
Usually replaces the OH with the Cl.
The chloride, the counter ion in that acid, is a good nucleophile, and it would do a substitution. I don't want a substitution, I want an elimination. So if I throw H2SO4 at this, that will modify the OH into a leaving group, so it will want to leave. That heat is now going to be pretty clutch, because the water's not going to really want to leave on its own. Why not? Why would the water not want to leave on its own? It's not negative. Because water in that case would be H2O plus, it would be positively charged. It would take the electrons and it would fix the problem there. Do better.
Primary carbon.
You would be forming a primary carbocation. Water's not going to be a great leaving group there. So that's where adding the heat can help kind of force that reaction into the elimination scenario. We will still have some water around within that solution that could act as a base to help pull off that hydrogen, but we cannot add a strong base in this environment because we need the strong acid to activate the leaving group. Okay? This could facilitate that elimination reaction. Is our yield going to be particularly great? No, we don't have anything to really pull that hydrogen off. We're really just kind of hoping and praying that probably with enough heat and time that we can get the reaction to go. Okay? Could we do something else to potentially improve the leaving group ability? Yes. We could run a substitution reaction. And if we ran a substitution reaction, we could do the substitution where the OH is no longer present and instead we have a bromine. And if we had the bromine, do we have an issue with our base? No. Okay? And so we could try and pull off something like hydroxide in our heat. But I think you have an issue with this.
Yeah.
What's the issue with it?
The octet and the tertiary wall.
There's no octet issues.
There is an H on the right side.
There is, but we don't care. You addressed this issue a little bit earlier on. Hydroxide is both a nucleophile and a base. With the primary leaving group, more than likely, what are we going to get? The OH is going to act as a nucleophile, not as a base. Primary substrates favor SN2. If we're going to do an elimination, it can work, okay, but it's not great. What can we do to limit that substitution? I don't want the base to act as a nucleophile. How do I change the base to make it less nucleophilic?
Turn it to water.
Then it's not a base.
Lessen the charge.
This is right up your alley. You love this answer.
Huh? What do you want about? Oh, okay, make it bigger.
Make it sterically hindered. If it's now sterically hindered, that's going to reduce its ability, okay, not reduce in chemical reactivity, but lessen its ability to act as a nucleophile and increase the odds of it acting as a base. For those of you being like, but we did 2-butoxide last time and it didn't work, I was addressing some of the issues potentially with it. Do we still have those issues? Yeah, actually we do. It still is a steric issue. But then we have the next issue, okay, that we encountered with the other one was that we had an acidic hydrogen on the oxygen. We don't have that acidic hydrogen to worry about. T-butoxide will be fine. It is going to be a slower reaction because of that steric hindrance, okay? But it would probably increase our yield than if we just went with H2SO4 and heat from the beginning. Probably. Okay? So depending on how you stacked this, it's entirely up to you. You could have done H2SO4 and heat, yes. Or you could run the substitution then followed by the elimination. Okay? How do we do the reagents for that, not the elimination because we nailed that one, the substitution? The substitution pathway that I just showed. How do we do the substitution alcohol for bromine? This reaction. All right, one option is HBr. Perfectly valid, lower yielding. Lower yielding because you're looking at that primary substrate, and HBr runs under an SN1 type mechanism. A little bit of peanut butter. Do a little PBr3. That PBr3 will facilitate that substitution very readily, okay, getting us to that bromine, which sets us up to now be a cleaner reaction for our elimination. That's exciting. We're now at 22 minutes. Man, that was an extra 13 minutes just to get a reagent. Okay, what happens in the next step now? Now we got to do the addition. Which, by the way, this addition is the one that I was like, I would have put an answer down for that immediately. I wouldn't have even waited.
HBr.
Yeah, I want to add HBr. Okay. It's placing the hydrogen and the bromine exactly where we want them. We don't need anything fancy. HBr works perfectly for that. What happens to the next one? I want to do an elimination again. Okay. Do I have this issue with the alcohol anymore? No, because I conveniently used bromine as a leaving group, and it's now only got that leaving group ability, which means what can I fall back on? My base and my heat. Okay. Does T-butoxide work?
Yeah. It's not the,
Is it the best option?
T-butoxide is indeed a base, and it will indeed do an elimination reaction. But where it's typically going to eliminate is to the less substituted product. It would actually be taking you backwards. We don't want to use T-butoxide in this case because it's going to do the opposite or move our chemistry in the opposite direction. So instead, what we would want would be a smaller base. We could even go as small as hydroxide. You could use ethoxide, methoxide. Okay. But dang, we tried that before, and Mike, as the evil person, was like, well, now you've got a problem with substitution. Do we have a problem with substitution now? This is, again, right up your alley, Anthony.
I know, I'm trying to think. No,
Why not?
because it's not sterically hindered. I don't know what you fucking want.
If it's negatively charged, okay, and we're thinking about the substitution issue, what mechanism are we going to favor with a strong nucleophile? SN2. Look at our substrate. What kind of substrate is that?
Tertiary.
That's tertiary. Does that run under SN2 reactions? No, not at all. I don't have to worry about the substitution at all. Okay? Because that is so sterically hindered that I don't have to stress about it at all. And that strong hydroxide will really only act as a base, run the elimination, get me the pi bond that I want on the internal as opposed to the external. Fantastic. Okay? And now, giddy up, we got the end. What did we add? For that last step? Yep, we added hydrogen and OH. What would be a good thing to do?
Water.
Put them together. Let's throw it as water. Okay, water's not a strong enough acid to activate the alkene, acid or electrophile to activate the alkene. So you always have to have some other active source. Okay, either a strong electrophile or an acid to activate it. Okay? And if we ran that reaction, where would the hydrogen go? Because the hydrogen is the most reactive thing. The hydrogen being positive, which of our carbons, okay, because I've been making Abby turn around and Josie turn around, we'll go back over here. Okay, which of our carbons is the negative carbon, the top one or the bottom one?
This is not.
It's the bottom one, because I would want a tertiary carbocation, which means where would my hydrogen go? Here. Is that where I want it to go? Nope. So H plus H2O recognizes what was added to the pi bond. That's good information. It's placing it in the exact wrong locations. Okay? And when we talk about the addition of H and OH across a pi bond, this is one that I've said both in this class and last semester. It's a critical one for you to memorize the reagents for, because there are 3 very common reagents, and they all do slightly different chemistries. That slightly different chemistry is what results in different products that come out, and because that's 3 different answer choices, you effectively have a multiple choice, a legit hard multiple choice question built instantaneously by doing the addition of H and OH across pi bond. Okay? So you need to be super aware of those 3 reagent conditions. We nailed one of them, H plus and OH, H plus and water. Okay? But what are the other 2? Okay? And cool, this is fine. This is a moment of, dang, I don't know. Okay? Anytime you hit a moment of, dang, I don't know, I've got to go look it up. That's fine. That's great. That's fantastic, particularly in a lecture or in homework. But what you need to have is a separate sheet of paper for those I don't know moments, so that when you figure out the answer, you can write it down there. Because that was something you needed to know to answer it. And if you don't know it, you haven't highlighted that fact that you need to review that content. So as soon as you hit an I don't know, you need to have a list. You say, oh, this was something I needed to know. Write it down. Okay? As you continue to practice or you get closer to the exam, maybe every week you can review that I don't know list and be like, no, I know that now. That was easy. That was stupid. Why did I get that wrong? Okay? Or damn, I really still don't know that. Okay. Now you can start to shift focus and be like, I really need to learn this. I need to memorize what's going on with this. It can help you be prepared for the exam rolling through. Okay. This is where note cards could come into play as well. Okay. While I was jabbering on, you all did some looking up. What did you look up? NABH4 is a phenomenal reagent to add H minus as a nucleophile to polar pi bonds. Is this a polar pi bond? No. So, not relevant. Little shaky. Because NABH4 can be used in other scenarios, but you've I don't know if you're using it correctly. So if you're just saying NaBH4, polar pi bonds, you're wrong.
Could use BH3 and peroxide.
The boron reagent, our BH3THF is a step 1, followed by a step 2 of peroxide and hydroxide. Okay, adds H and OH across a pi bond, and it adds it in the anti spots. We would place those atoms where we would not expect to place them. Why? What charge is the hydrogen being added in our very first step?
Negative.
As a negative, which means the negative needs to go to the positive. Which carbon did we say was the most positive?
Tertiary.
The tertiary one. That's where the hydrogen goes. That's exactly what we want. Once the hydrogen is on there, the oxygen didn't have a choice where it has to go, and it's now forced into that other spot. So the chemistry goes opposite the way we would expect. Okay? Added wrinkle behind this. Taking a look at that product, what stands out as potentially problematic? We have stereochemistry specified within that. If we're talking about BH3 and THF, yes, they are adding H and OH across the pi bond, and it adds it in this anti-configuration, but it can add it to the same side of the pi bond?
Is that on opposite sides of the body? Or like opposite, one is above and one is below. Oh shit.
That's challenging because we would say opposite sides because we think of how the chemistry is working. But if you think through how the chemistry works in this particular case, it's forced to add to the same side. That's all of those stereochemical considerations of how the boron interacts with the electron source within our structures, and it places the H and the OH on the exact same side of the pi bond. We get a syn addition of those two reagents. Okay, that is absolutely a tricky piece. So for me right now, I would be in your spot taking notes. BH3THF, motherfucker, H and OH, and it adds to the same side. Okay, it's your choice. You do whatever you want to do. But all I'm trying to do is call attention to an opportunity where you could now identify that piece that you were missing so that you have an opportunity to review that. If you decide to not do that, you're minimizing your opportunity for that review process prior to the exam. That's all that I'm putting out there. Okay? Trying to give you the opportunity to find ways to be more successful. That's it. Okay? So far, so good? What's the other reagent? And of course, yes, it is the wrong reagent.
I know that OH doesn't do as a radical on opposite sides.
What?
I thought BH3 THF and H2O2 like reacts as kind of like a radical.
I don't believe that mechanism, even in its full truth, runs as a radical reaction. What you might be thinking of is that when you see BH3 and THF, there's always this big dot there. That dot isn't signifying a radical. What that dot is signifying is a complex structure, that the BH3 is directly integrated into the THF. Okay, that they are parts of each other. Okay. To get the chemistry happening, excuse me, in an addition reaction the opposite the way you would expect, there is an alternative. Instead of doing this in one step, you could do a radical addition of HBr. The radical addition of HBr would place the hydrogen and the bromine in the opposite locations, and then we would try and run a substitution reaction to get the bromine where we want it. Okay? The problem with that is that's going to force a backside attack. That's not going to get your alignment of the H and the OH where you want it to be. Okay. It's a little bit more complex than that. But you could break up that addition into two reactions. One, a radical addition followed by a substitution. It's going to mess up your product distribution, though. So again, back to my question, what other reagent adds H and OH? It's up to you. It's fine. Just trying to help out. Okay. And this might be where your sodium borohydride was coming in, your NaBH4. Okay, what you should be memorizing is not NaBH4 for the next reagent, it's mercury. Okay, the HgOAC in the presence of water or an alcohol will go through and add technically all that adds is the mercury and the oxygen to your structure. Okay, and you follow that reagent up with sodium borohydride to remove the mercury and place the hydrogen. Okay, so if that's what you were referencing, you had part of it, but you had probably the least relevant part, unfortunately. Okay? Kind of, sort of? Questions? Because this was yours. Are you satisfied?
For the last part, you do HgOAC with NaBH4 and
For the last step, you do exactly what is specified up here. What I followed up with was what was the third reagent that adds HNOH. The third reagent that adds HNOH does not add it where you want it to be added for this reaction, so it is not useful. Okay? What the question was is, do you know all of the reagents? Because are you going to need them? Yes. 100% you will need to know those reagents. All the reagents that add HNOH. Okay? So if you're trying to prepare for an exam, and since you're looking at the practice exam, I'm going to say you probably are, you need to know those reagents. Since you didn't know them, we had to talk through them. So I told you what those reagents were. You should now have that list so that you know to review that information prior to the exam. Yes?
Is there any way we can go to and also that same dilation with the epoxide, and then as happens that is substituted as part of the epoxide?
If you wanted to do an epoxide.
Is that possible?
Yes, the epoxide, I think, can get you the HNOH. The challenging part is you need to get the H to come in there, and that H needs to come in as a minus. I believe you can pull that off with the sodium borohydride, sodium borohydride or lithium aluminum hydride to bust open epoxides. The problem with that is you're adding a strong nucleophile. The strong nucleophile is going to attack the least sterically hindered site for that epoxide, placing the H and the OH in the wrong stereochemistry, okay, or the wrong regiochemistry. On top of which, because you have that epoxide, the H has to come in from the backside, you'd get the wrong stereochemistry as well. Okay. So I believe you can get that one to react, and you're relying on kind of the reactivity of the epoxides in the presence of your borohydride or lithium aluminum hydride. Okay. So that is another alternative to potentially pulling that off. Much less common, but yes.
So for the last one, you said what's the third? Like, are you adding the HgOAC? Because you have the pH3 and the H2O2, you said that's on opposite sides, not the, or same side, not the opposite side.
Look at your answer. Do you want them on the same side or on opposite sides?
Opposite.
What are you adding when you use the BH3 and the THF? What are the two pieces you add when you use those reagents?
The HgOAC.
When you use these reagents, what is added across the pi bond? Okay, so this reaction, do you see Hg?
No.
Don't reference it. What does this reagent add across the pi bond? H and OH, fantastic. Okay, how did it add it?
Opposite.
Okay, where's the H? Wedged or dashed? Dashed. Where's the OH? Dashed. Did it add it on opposite or same sides? Same sides. What does the BH3 and the THF and all that reagent do? It adds the H and the OH, opposite regiochemistry of how you would predict, and syn addition, same side. Does this reagent work for this?
Yeah.
Yes. What did I ask about for the addition reaction? When we look at the addition reaction, we noted that what did we have to do? We had to add, we had to gain a hydrogen, and we had to gain an OH. And what I said was that there are 3 reagents that do this. Okay? You picked out one of those reagent sets. H plus and H2O. What happened when we add H plus and H2O? But everything's going to add on opposite sides. True. This does a standard addition. Okay. Standard was defined by somebody. Who defined standard?
Is that Markovnikov guy?
I butchered the hell out of that. Kov. Nick. Fudge. I can't spell. Okay? That's what we suggested. Didn't work. And I said, there are 3 reagents that do this. 3 reagent sets. What are those 3 reagents? That's what I asked. What was the response I got? Yes, very good. Silence. Okay, which meant we didn't know it. And I said you needed to spend some time to figure out what those reagents were. And I talked through, hey, we hit this silence wall. What does that mean when we hit a silence wall? That means you're missing something, which means you need to have a sheet of paper out in front of you so that when you miss something, you can write down, dang, I need to memorize this later when you figure out what that thing was. During that interlude, Abby spent some time and looked it up. And when she looked it up, she said, hey, one of those other reagents is BH3THF followed by sodium hydroxide and H2O2. What was the result of those reagents? It adds the H and the OH opposite of our standard. Is that what we wanted?
Yeah.
Yes. Okay. We then added the wrinkle. Ooh, there's regiochemistry, or not regiochemistry, stereochemistry. Where are the H and the OH added? Oh, they're added on the same side. Does this reagent add in a syn addition? Yes. So we said a syn addition. Okay. Again, focus, addition, H and OH. You need to know these reagents because you absolutely 100% will see at least one question, if not more, on this. Because that's 3 and you think, your multiple choice, how many answers do you have in your multiple choice? 4. You have 3 very good answers. All of them add H and OH, which means that's a really hard multiple choice if you don't know those reagents, which means you need to know those reagents. Because we had silence, I asked again, what was that 3rd reagent? And that was the response again. So what did I do? I said that 3rd reagent was HgOAC, okay, an alcohol or water. In this case, we want water, followed by sodium borohydride, okay, officially HOAC2. These are the 3 reagents that add H and OH across a pi bond. How does the mercury one add? Well, I didn't know that reagent. Okay, then accept that and announce, I don't know that one. It adds the H and OH. Standard chem. This would be Markovnikov. There we go, a little bit better. Okay? The BH3 would be anti. What we've now done is specified this secondary chemistry so that you have that at your disposal to answer future questions. Because lecture isn't about answering this question, because how often will you see this question?
No, never again, probably.
And if you never see it again, answering this question is useless. You have to extrapolate beyond. That beyond process is how do we look at all those pieces? That beyond process is how are there different reagents? Are there particularly different reagent systems that we really have to be worried about because they have a natural multiple choice question built out of them immediately? Yes, they do. So pay attention to them. It adds H and OH, standard Markovnikov. Where does the H and the OH go? Are we concerned about stereochemistry? Right? And if we didn't remember that one, that would be fair. We may not know.
Well, doesn't that make it where it's opposite stereochemistry?
This one becomes kind of strange. It adds as a giant mix. Depending on which stage of the reaction you're at, you're going to get a mix, which ultimately means when you look at the product, the H and the OH go everywhere. So you don't need to worry about it. So when we look at the mercury reagent, stereochemistry becomes an irrelevant fact. The BH3, very important, right? Because typically when you're being asked about the BH3, they're almost always harping on that syn addition, okay? Because that's a retention of stereochemistry, and that's nasty, okay? So is there something else we should worry about? Of course, there's always something else to worry about, Mike. Stop being a naysayer. Naysayer? Am I a naysayer? One of those things. I have two reagents that do standard chemistry. Why do I have two reagents that do standard chemistry? Why do I need to be worried about two reagents that do standard chemistry?
Because the mechanism in which they do so is different.
And if the mechanism is different, what might else also be different? The products that come out of them. There may be a complication of one versus the other that limits or prevents certain secondary systems from happening. What's that big deal? When we add the H plus and H2O, we go through a carbocation. And what do we know about carbocations?
They're not stable.
True, they aren't stable. It's true, more letters in resonance.
Hybridization.
What's that?
Hybridization.
No. Fuck's not the answer either.
Rearrangements?
As soon as you see a carbocation, you should immediately be thinking of rearrangements. Because you don't get a carbocation in the boron reagent or in the mercury reagent, you don't get rearrangements. When you add H and OH in the standard addition, you absolutely have the potential for rearrangements. And it just says rearrangements. See? Fit perfectly. Okay? Those three reagents, this is probably the third time we've talked about them, okay? Particularly in this level of detail. Okay? Will it be the last? Probably not, if we're going to be honest. Okay? But hopefully the next time around, you will have memorized some of the bits and pieces so that by the time it rolls around on the final, you will have had all of those bits and pieces memorized so that that question is a lightning round, easy question for you to answer when it hits you on the final. I should also add, there's no guarantee that they will ask it. It's just, if I'm going to write a test, That's a question that writes itself. Questions about any of that? Okay. What's next? Don't look. I got to it a lot faster than I thought I would. We're gonna pause this though. Maybe. Retrosynthesis. So in retrosynthesis, what we're being asked to do with this arrow, whoops, as I erase it, with this arrow is think backwards. This is the product. I want to know the reactants. Why did we not write it? I already forgot what the structure looked like. God damn it. The other way, like this, whatever that was with the stuff and the thing and the dance. I don't know. I really don't. I find it annoying. I don't get it. But that's not a problem we get to solve. It's a problem that we have to deal with. So this is how it gets formatted. So you need to be familiar with that format. So how could you go through and do this?
Just go ahead and react each of the
Okay.
answers.
One method to solving this is exactly what you suggested, which I would argue is hardcore brute force.
Oh, yeah.
Okay? This is, oh my God, that is way too flippin' hard. I don't want to think about that. I'm going to look at A and say, what could I do to make this happen? What would happen if A reacted? Nope, that didn't work. What would happen if B reacted? What would happen if C reacted? What would happen if D reacted? Okay? For the sake of time, I'd argue that's probably the easiest. Okay? Because the other approach is really kind of nitpicky, looking at the details behind that reaction and hoping you can pick out the active new bond that was formed. Okay? And that's hard. Is that a question?
Well, would it be C? Because like with the, I guess with the method you showed before, it's kind of just like attaching the two structures based on the negative carbon site and the ketone site. So secondary would be the negative
Okay.
carbon.
Cool. So I like how we started that. The answer is C, because that's what you've taught me, Mike.
Well, one has 3 oxygens, the other one has 2. I think that's all we need.
So if we go through and look at this reaction, what do you see as the most reactive? So what we're going to do is do a little bit of hybrid here. And I've been saying, well, Mike told me I think it's C, so I'm going to go do C as my answer, and then we'll follow on with Abby's method, because Abby was brute force, let's just hit it and see what happens. Okay, so a little bit nuanced. Okay, instead of going with A, B, C, D, we just went C, let's do it. Okay, so what's the most reactive thing? What's that? The carbonyls are partially positive. I will accept that. What's the most reactive thing? This is the what? The alpha hydrogen. Cool. It's the alpha hydrogen. Well, there's one there. There's one there. There's one there. I'm liking your suggestion less and less. And there's one out there. So the alpha hydrogen, huh?
Yeah. The green one is the most reactive. Because it has two carbonyls next to it.
Okay. So in that grand scheme, maybe you said the alpha hydrogen because you were like, I recognize that that green one has the opportunity to do double resonance, which would stabilize that conjugate base significantly more than any of the others. So when you said the, you were like, stop being an asshole, Mike. It's just the green one. Okay. For the record, no. 2 people got that. That's all that matters. Okay. Now what?
Would react with the other positive.
Okay. It's technically reacting with the oxygens that are right next to it, those carbonyls, through resonance, which means those are not particularly active. And so what's going to happen instead is it's going to have to react with the other partial positive. So identifying that those carbonyls are reactive, spot on, lovely. We have that chemistry now built out for us. So we can now start to draw this out. And you might be like, God, this is going to be a effing ugly molecule. Dude, you can't look at this structure as a product and be like, yeah, it's going to be pretty. Okay? So you should be able to look at that and be like, yes, this is just going to be an ugly, ugly, ugly system. And there isn't anything we can do about it.
Yeah,
We
but
should
I
just
don't
hurt
think
the
it's gonna
feelings
be-
of the molecule.
I think it's going to be a riot thing for the molecule.
Whoops. Right? Because it hits and breaks open the pi bond. Okay, and now what's your thought?
It's too many oxygens. I think that's the first thing that pops up.
Okay. First thing that pops up is too many oxygens. Okay, except what could you potentially do with this structure? It's technically a lie. I thought there was something else you could do with it, and it turned out to be wrong.
This is
What kind of chemistry is happening here?
a whole lot of hoopla.
That's a bit of an overstatement. I would argue this fits right up the alley of the aldol reaction.
Oh.
You've got an alpha hydrogen, you remove that alpha hydrogen, it attacked a carbonyl. We're looking at an aldol type reaction. When we look at aldol type reactions, what do they typically do? They usually condense, but they condense because, what's that? There's a second alpha hydrogen.
Oh, and this one really isn't.
Because you would take those electrons, shuttle it in, and kick that group out. Okay? Which, and I know, give me a second, okay? Which, if we did that, would we have too many oxygens? No, we'd have the proper number of oxygens, okay? But,
You don't have a second.
yeah, by drawing that hydrogen on, we've exceeded the octet. We don't have that second alpha hydrogen, which means that elimination isn't possible for us, which means we'd be stuck with
That.
3 oxygens. Okay. Maybe we do a reduction. I don't know. Okay. If we did a reduction, would that get us to our potential product?
No. No, I don't think it would.
So there's 2 carbons. And then I got this guy, which is connected here. Ah! Wrong button. Sorry, I just yelled at you. That's for anybody who watches the video, which would be connected out here. You guys have a large enough space. The yell isn't quite that bad. So what does that suggest?
This is wrong.
That Mike was wrong, because our explanation for C was that Mike said that that was the answer. Okay, so Mike was wrong. I accept. Okay. So what now? Well, one thing, we could delete C. Ta-da, that's nice.
And can we do D as well?
Why do you want to delete D as well?
Because it has the same problem.
Yeah, D is going to introduce the same issue. You still have that alpha hydrogen. That one's going to be the most acidic. If that one reacted, you can then go through and talk about where it's going to react, which is going to be a whole nother beast. We should lean on that. We could lean on that a little bit, but then D looks pretty problematic as well for that kind of same reason. That's going to be now making that connection up to that thing. You're going to have that carbon connected to 1, 2, 3 carbons. And that carbon in our ring structure is only really connected out to 2 carbons. For those of you that can count, I apologize. There's that 4th carbon down there. Okay. So that would suggest D is also wrong. So awesome. Okay. By attempting this brute force, we picked up a little information along the way to suggest that another answer is wrong without having to drive into it. That's cool. I like that. Okay. And actually, as we push on that a little bit more, right, we just went through and said that that was negative. Where does the negative then react? With the partial positive. And what does this particular product add to it that the previous one did not? Does that additional pi bond introduce another partial positive? Why, yes, it does. Okay. And that extra information may be a useful tip-off, because if we go back and look at A and B, what do A and B also have in common? They also have that additional pi bond where we're introducing that. Okay. That alpha-beta unsaturated carbonyl. Okay. So a little bit of work. I think the last video stopped around, oh, we're at 60. So I was going to say it was only like 2 minutes to answer that, but no, I think it was closer to 10. Okay. So what do you want to try now? Coin toss. One person says B, one person says A. Okay. Who's the favorite student? You all are. Do it on the boards.